All right, welcome back to Easy Math with Nick. I know it's been a hot minute, but we are back on video number 21 today. Today we are doing an E&M question from last year's exam, the first one. I remember doing in a recent video, well, how recent could it be, but in a semi-recent video, we did the first free response question on the mechanics exam. So I figured today we do the first one on the E&M exam from last year as well. So, and I try to do what I think is the ampersand symbol. But I think I just did a cursive capital J instead. Whatever. Don't worry about that. All right. An isolated air-filled charge capacitor consists of two conducting coaxial cylindrical shells. Any calculus students probably have PTSD from that, but that each have length L. The inner shell has radius R1, and the outer shell has radius R2. As shown in Figure 1, where R1 is less than R2, is much, much, much less than L. Surface charge densities, amount of charge per unit area, nice that they tell you that, of the inner and outer shells are positive sigma sub 1 and negative, so the inner shell has positive charge, the outer shell has negative, so that's what they're telling you there. The absolute values of the total charges are equal. Okay, that's nice. Okay, so using Gauss's law, derive an expression for the magnitude E of the electric field as a function of the radial distance R from the center of the capacitor for the region between R1 and R2. Express your answer in terms of R1, sigma, R, and physical constants. Okay, so when we use Gauss's law, we want to choose a Gaussian surface that allows us to set up our integral, and so we can have a constant electric field along the surface of the Gaussian surface that we choose. So then we can take the electric field out, then integrate that dA. So Gauss's law states that the surface integral of E dot dA is equal to the enclosed charge over, this is called vacuum. It's a constant, over a constant that's on your equation sheet, which is like E naught. We call it E naught. So when we choose our Gaussian surface here, I think it's a quite easy choice here. If we look at our cross-sectional view, we're going to choose another coaxial cylinder that's sort of sandwiched in between those other two. And so it's going to have the same length as those as well. And so what that's going to allow us to do is electric field is going to be constant at the surface of this because each point is the same radial distance away from the inner cylinder. So this is a good one to use. So we're going to use a cylinder as our Gaussian surface here. And so when we look at the surface area of a cylinder, we know that it's 2 pi r L or 2 pi r h plus 2 pi r squared. Here, we're not going to worry about the 2 pi r squared because that represents like the caps of our cylinder here. But if we look at the electric field to the at the caps of the cylinder, it's sort of parallel to the surface of the cylinder, which means when we do E dot dA, we're going to have E dA. Oh, well, the angle between them is 0, so it's going to become 0 because we'll have, I think, E dA sine theta. This is technically why we don't look at the end caps here. And theta 0, so sine 0. So that's why we neglect the end caps here when we integrate dA in just a short second here. So if we solve now, if we start to solve, we'll factor out E because E is a constant at each point on the Gaussian surface. dA equals the enclosed charge. But what is the enclosed charge, you might ask, right? Well, we saw before that the surface charge density is Q1. And they tell you this as well, amount of charge per unit area. So amount of charge per unit area. So this will be the enclosed charge all over the total area, the surface area of that cylinder, which is what? 2 pi R1 L. There you go. So that's going to be what that tells you, and then we can solve for the enclosed charge. Because when we choose our Gaussian surface, the enclosed charge is the charge on this cylinder here. I'll use a different color. On the cylinder of radius R1, right? This is all our enclosed charges on this cylinder. So that's why we're able to use the surface charge density here by saying, oh, what happened? No. Ooh. That was work. No, we're not. We didn't lose too much here. But as I was saying, on our surface here, this is all of our enclosed charges on that. So by using our surface charge to sigma 1 equals what was it, Q enclosed over 2 pi, they call it R1, and length, we'll call that L. Oh, I mean, they give that to you. So if we want to solve for an enclosed charge, multiply both sides by the denominator there, we're going to get sigma 1, 2 pi R1L. So this allows us to substitute that up there now. So once we do that, we'll get, we'll take E out again because we forgot to do that. Well, no, I forget to, but we lost our work, unfortunately. So sigma 2 pi R1L over E naught, which is just a constant. So we'll have E times, this was our discussion about when we integrate that area differential or our area vector. That's going to be, and we chose our, when we chose our cylinder here, our Gaussian surface cylinder. We chose that. I'm not going to explain that again, but we get 2 pi little r because now our Gaussian surface, we have a radius that's just little r. We choose what we want that to be because as a function of the radial distance. So that could change up until r2. So if that makes any sense. I know I sort of glossed over that, but a little bit, which we lose our work, but it is what it is. So our 2 pi's cancel. Now that we're trying to solve for E, remember we want the electric field, so don't forget what our end goal is here. And also L's cancel. Notice how they didn't tell you that your answer would be in terms of L because it cancels out. So they sort of anticipate that. R is not canceled out, by the way. So again, answer of sigma R, big R, over little r, no. There you go. I think that's our answer. That should be right. Yep, that looks right to me. Okay, let's move on to part 2 of A. Derive an expression for the absolute value delta V of the potential difference between inner and outer shells. Oh, this shouldn't be that bad. So we have electric field, and now they're asking for a potential difference. Well, we know that E, electric field, is equal to the derivative, the negative derivative, of potential difference with respect to time. Potential with respect to time. So if we rearrange this, disregarding the negative, because they just asked about the absolute value, okay, dV equals E dt. I know this really isn't a fraction, but you can sort of treat it that way. Beyond the scope of this video. So then we integrate both sides. We get V equals integral E with respect to time. So, I'm sorry, not with respect to time, with respect to distance. I lied, I'm sorry. With respect to distance. So dr or dx. We'll say dr here, because we're working with radius. So this is what we want to use here. It's not your answer, but. So if we want to find that potential difference, where are we integrating from where to where? Well, potential difference between the inner and outer shell. So the inner shell has a radius of what? R1. The outer has a radius of R2. So we're integrating from R1 to R2. What was our electric field? That's what we got in the last problem, right? R1 over R E naught with respect to radius, not time. So don't do what I did. And we should really say absolute value because there should be a negative there if they wanted that. But so everything I'm going to circle in blue here is a constant. So all of this, no. That's not what I meant to do. All of these are constants, so we can bring those out of the integral. So because big R1 is just the radius of the the inner shell. So we can pull that out. 2, 1 over r dr. If you don't know this integral, what that is, it's on your equation sheet, but you should know it because that's ln, the natural log. So we're going to get absolute value. Absolute value isn't of too much importance here because we're dealing with radii, which are positive by nature, so we don't really need that. So R1 to R2. We're not running out of space here, right? Nah, nonsense. So we'll have ln R2 minus ln. I say ln, I should say natural log, but whatever. There you go. And we know by property of logs that this is going to condense down to what you're about to see. R2 over R1. There you go. And this is going to be your answer for that question. All right. So this is an interesting one. On the axis shown in figure 2, sketch a graph of E as a function of R from R equals 0 to position as outside the outer shell. So all right, this one requires quite a bit of thought. So before we hit R1 is this radius here, right? I'm going to represent with the red dot. It's this radius right here. Before R1, because these are shells, there's no substance to the shell inside this region here. There's going to be no charge within there. So when we do Gauss's law, there's no enclosed charge with a radius smaller than R1. So that inner area has no charge, and thus there's going to be no electric field for that region. So the graph is just going to be 0 for that region. Now, if we're looking between R1 and R2, well, we have a function for that already, right? It's this. It's going to be decreasing because this is like a 1 over R relationship. So we're going to start at some maximum value and then start decreasing. So what is that maximum value going to be? They don't tell us to label it, but it would be, if we plug in R1 to this, we would get sigma 1 over E naught because the R terms would cancel. So we're going to start at some maximum and then keep decreasing from there. So that's going to look like this. All right. And now beyond R2. Okay. R2 now introduces some negative charge. So how is that going to change this, right? At R2, now we're looking at the outer shell. That outer shell has a negative surface charge density. So when we do Gauss's law over here, our enclosed charge is going to be less now. The magnitude of it's going to be less because we started with some positive charge now, and now we have more negative charge because this has a greater surface area, right? The outer one has a bigger radius, so it's going to have a greater surface area. So greater, so we're going to have Q1 minus Q2, and if Q2 is greater than Q1, when we subtract them, we're going to get something, unless Q2 is much greater. They don't tell you, but we can assume that it's not that much greater. We're going to get, we're going to have less magnitude of charge, enclosed charge now, when we include that outer shell. So the graph should, you kind of have to make the assumption here, but it's going to like dip a little bit and continue having that 1 over R relationship as we get further away from the cylinders, the outer shell. We're going to approach, our electric field is going to approach 0 as we get farther away. Okay. A material of dielectric constant K is inserted into the isolated charge capacitor such that the material fills that region, as shown in figure 3. Determine the capacitance of the C of the capacitor with the material inserted in terms of those things in physical constants as appropriate. Begin your derivation by writing a fundamental physics principle or equation from the reference. Yada yada yada. Okay. So we know that a relationship that we could use here is capacitance equals E naught A over D times the constant kappa, dielectric constant. So this is the when they asked equation from the reference information, this is what you would start with here. And D is the distance between plates, which is, what is it here? It's R1 minus R2, right? Because R2 is this total thing, and R1's this. So we subtract them to get this region here. I didn't really show that very well, but hope you get the gist of that. So, oops, why did I do that? E naught A over R1 minus R2 minus R1, sorry. Times K, but there's still something here that we need. A, what is A? Area, that's going to be the area of the smallest capacitor plate. Usually you would use this equation when you have like parallel plates, when you have like two rectangular sheets and then a dielectric between them, sort of like a sandwich. Haven't ate lunch yet, so I'm hungry. But that would be that would usually when you use this, so you wouldn't think about which has a smaller area, right? But in this case, the inside shell is going to have a smaller area, so that's the area we use in this equation here. So what is the surface area? Glad you asked. We sort of dealt with this before, right? It's just going to be 2 pi r1 times L. We neglect the end caps for the same reason as before. Well, not really the same reason, but we just want the surface area that has, well, an electric field on it. So we're going to have that times 2 pi r1L. We'll put decay on the top now. R2 minus R1. And that should be your answer. There you go. I don't see another way to do this because if, yeah, I don't know. You have to have it in terms of what they give you. So we're in terms of L. Have an L in there. We have R1 and R2. R1, R2. And then we have K. That is everything. So we should be good. That should be your answer. So that was it for this question. Sort of a short one, but took 15 minutes to solve it. I think that's about how much time you have anyway. So I think you had a good pace even with me explaining it as much as I did. So hopefully that one made sense. I think that's it for this question. So this was video number 21. We the first free response question on last year's Physics C E&M exam solved. Hopefully everything was pretty clear. And thank you for watching. We'll see you on the next video. And there you go. See you then.